module 9 we are going to discuss various integral transforms, and by integral transforms I mean Fourier transforms and primarily Fourier transforms, but there are also other transforms like Laplace transforms, and there are actually several other transforms. But we will primarily be focusing on Fourier transforms because that is one part of mathematics that is very useful in solving various differential equations. And in fact, we will also show that the Fourier transforms is a way to understand some of the foundations of quantum mechanics like the uncertainty principle. So, we will discuss all these in this module, and I will start the first lecture by introducing the Fourier transform. So, a good way to understand Fourier transforms is to think of them as extensions of the Fourier series for a function that whose period is actually going to infinity. So, when we did the Fourier series, we said that we wrote the Fourier series as in the following way. So, we wrote f of x, I will use the complex form, and you said sum from n equal to minus infinity to plus infinity, and we said it is e to the I into 2 pi by L n x, okay, and this times C n, we had a coefficient C n. Okay. Let me put the coefficient before the exponent. Now, let us highlight a few things. First is L, okay, this represents the period of function. Okay. So, the period of function is L. Okay. I had alternatively used 2L as the period, but in this case I am using L as the period of the function. So, what you have is f of x equal to f of x plus L. Now, you can ask the question, what happens if we let L go to infinity? If we imagine that that L is going to infinity, what will happen? Okay. So, that is the idea of the Fourier transforms. Now, let me write this in a slightly different way. I will write this as sum over. Okay. Now, I will call this factor of 2 pi n by L, I will call it as k, okay, and instead of C n I will use C k e to the I k x, where k is equal to 2 pi by L into n, okay, and as n goes from minus infinity to plus infinity, k will also go from minus infinity to plus infinity. So, k equal to minus infinity to plus infinity. Okay. However, k is not k, the spacing in k, spacing between successive k values is 2 pi by L. Okay. So, that means if n equal to 1, then you will have 2 pi by L. If n equal to 2, okay, then you will have 4 pi by L, okay, and the difference between 2 pi by L and 4 pi by L is 2 pi by L. So, between any two successive values of n, okay, the spacing is 2 pi by L, the spacing in k is 2 pi by L. Okay. So, we will just make a note, we will say delta k equal to 2 pi by L. Now, this already motivates us to think about what happens if L becomes very large. So, if L becomes very large, delta k becomes very small. Okay. And if delta k is very small, that means you have k values that are very close to each other. Okay. So, the successive k values are very close to each other. So, this sum, okay, will be related to an integral. Okay. I am not saying it is equal to an integral. Okay. So, what you can see is that if the successive k values are very close to each other, then this will look like an integral with this factor of delta k. Okay. So, this motivates us to the definition of the Fourier transforms. So, now we will write the definition of transform. So, when you have k being very closely spaced, okay, then what you do is you write f of x is equal to integral from minus infinity to plus infinity, and we take a factor of 1 over root 2 pi. It will become clear why we put this factor. You have e to the I k x f of x dk. So, you are integrating over the variable k, and you have e to the I k x f of x e to the I k x f of k dk. Okay. Now, just notice the similarity between this expression and what we had here. Okay. So, instead of a sum you have an integral. Okay. You have this factor of 1 by square root of 2 pi. Now, instead of c k I am calling it as f tilde of k, okay, and the reason for that will become clear, and you have e to the I k x. So, basically you can see that the Fourier transform is like an extension of Fourier series for when the period goes to infinity. Okay. Now, I call this as f tilde of k, okay, instead of calling it as c k, I just call it f tilde. I wrote it as a function of k because k is a continuous variable. Okay. Now, when you write a Fourier series, when we write a Fourier series, one of the things that we note is that you can write C n as sum over I can write C n as integral f of x e to the minus I 2 pi x n by L dx. Okay. So, I can write C n in this form, okay, and x goes from 0 to L and 1 by L. Okay. So, this is what I can write your C n as when you write a Fourier series. Okay. Now, the same way now notice C n is written as an integral over f of x, and you have this. Okay. Now, by the same argument I should be able to write f tilde of k, okay, you can show this, okay, as 1 by root 2 pi integral minus infinity to plus infinity e to the minus I k x f of x dx. Okay. Now, actually you can see why the factor of 1 by root 2 pi is there, okay, that is here because now it makes both these Fourier transform and the inverse Fourier transform look very symmetric. So, the only difference between the two expressions, in one case you had e to the plus I k x, in the other case you have e to the minus I k x, okay, and you integrate in one case over k and the other case you integrate over x. Okay. So, this f of x and f tilde of k they constitute a Fourier transform pair. Okay, that is f of x is the Fourier transform of f tilde of k, and f tilde of k is a Fourier transform of f of x. Sometimes this, the second expression is called the Fourier transform, and this is called the inverse Fourier transform. So, this might be called the Fourier transform, and this is called the inverse Fourier transform. But actually there is I should emphasize that it is best to think of these two as a Fourier transform pair. So, if you call one the Fourier transform, then the other will be the inverse Fourier transform. Okay. So, this process where you convert a function of x to a function of k is called Fourier transform. So, you write f tilde of k. So, you start with a function of x, convert it to a function of k. Okay. and that is called the Fourier transform. Then you take the function of k and convert it back to a function of x, that is called the inverse Fourier transform. Okay. Now, there are a few conditions. Okay. So, so conditions for existence of Fourier transform. Okay. So, condition for a so this integral exists. Now, if you take the absolute value of this integrand, okay, absolute value of e to the I k x is just 1. Okay. So, so the conditions for existence is that f of x should be absolutely integrable. So, so that means integral f of x absolute value of x dx from minus infinity to plus infinity should be less than infinity. Okay. That is a condition, and in other words f of x should be piecewise continuous. Okay, this is an important condition. Okay. It need not be continuous, it can be discontinuous, but it should be piecewise continuous. Okay. So, so what that means is that you can have a function, if I just plot it right here, a piecewise continuous function might look, so if I put x and f of x, a piecewise continuous function might look something like this. It might look something like this. So, it is not continuous, there are points of discontinuities, but the points of discontinuities, there are only finite number of these discontinuous points. Okay. So, that would be a piecewise continuous function. So, if you can do this integral, if this integral is less than infinity, then here you are just multiplying it by some quantity whose absolute value is less than or equal to 1, or it is equal to 1. Okay. So, that integral will also exist. Okay. So, this is the condition for existence of Fourier transform, and in general, you know, the Fourier transform is something that we assume exists for various functions, and we try to calculate. So, let us look at some examples. Let us look at Fourier transform of some functions. Okay. So, suppose I have f of x equal to, now if I have e to the minus x, okay, so this you can see that e to the so this function goes to infinity as x tends to minus infinity. So, when x goes to minus infinity, this function goes to infinity. So, Fourier transform does not exist. Okay. This is the first thing. So, you cannot take Fourier transform of e to the minus x. So, what about so now this is the first example. Now, let us look at a slightly modified function f of x is equal to e to the minus absolute value of x. Okay. And let me put a constant k here. Okay. So, just to say that you know you have some factor k times absolute, or not k, let me put alpha times absolute value of x. Okay. So now let's if you just had e to the minus x, your function look like your e to the minus x looks something like this. This is e to the minus x. Now, on the other hand, if you take e to the minus absolute value of x, then it looks like this. Okay. So, and now so this, so if you put a factor of alpha, it will essentially look like this, and you can clearly see that this integral is finite, where this integral goes, the integral under this function goes to infinity. Okay. So suppose you take this, now let us evaluate the Fourier transform. So, f tilde of k is equal to 1 over square root of 2 pi integral from minus infinity to plus infinity e to the minus alpha absolute value of x times e to the I k x dx. E to the minus I k x. Okay. So the assumption here is that alpha is greater than 0. So 1 over root 2 pi of now alpha is greater than 0. So, I can split this integral into two integrals. Okay. So, I integrate from minus infinity to 0, and from minus infinity to 0 x is negative. So, absolute value of x is minus x. So, you will have e to the plus alpha x minus I k x dx, and then you have plus integral from 0 to plus infinity, and now you have e to the minus alpha x minus I k x dx. Okay. So, now you can do this integral by treating this alpha. So I will do this integral, I will just, so e to the x alpha minus I k divided by alpha minus I k. Okay, so I will just write this integral in this form. So, I just did the integral of an exponential, I just treat it like a regular exponential, and I do this integral, and now the limits here are from minus infinity to 0 plus the same thing, okay, e to the minus x alpha plus I k by alpha plus I or minus of alpha plus I k, and this integral is from 0 to infinity. So now we can put the limits, and we can go ahead and calculate. So, when x equal to 0, this becomes 1. So I just get 1 over alpha minus I k. So, now when x goes to minus infinity, okay, this is e to the minus infinity. So, e to the minus infinity is 0. Okay, so e to the minus infinity is 0. So that the you will just have a minus 0 plus 0 minus 1 over minus of alpha plus I k. Okay, so these are the terms. Okay, so I can write this as 1 over square root of 2 pi, okay, and I have 1 over alpha minus I k plus 1 over alpha plus I k, and I can write this as 1 over square root of 2 pi. Okay. Now, I get if I just multiply it out, I will get 2 alpha divided by alpha square plus k square. Okay. So this is the Fourier transform of Fourier transform of e to the minus alpha absolute value of x. Okay. So this illustrates how to take Fourier transform of a function. I will take one more example. Again, this is a very commonly used Fourier transform. So here I take f of x, okay, as I take e to the minus alpha x square. This is a Gaussian function, and in this case I can go by the same argument. So, f tilde of k is equal to 1 over square root of 2 pi integral from minus infinity to plus infinity e to the minus alpha x square e to the minus I k x dx. Okay. And if you can work this out exactly the same way. So, you write 1 over root 2 pi, and what we will do is we will use a very popular method in solving these Gaussian integrals. Okay. So, this is called completing the squares. So, we will write it as e to the minus alpha x square plus I k by alpha x. Okay. And so now if you complete the squares, if you want to write this as a perfect square, then you will write I k by 2 alpha whole square. Okay. And what you have to do is since you added this term, you have to subtract the same term. So, what you will do is multiply it by e to the now we will write plus alpha times I k by 2 alpha whole square dk or dx, sorry. Okay. Now, you notice that this last term is independent of x. Okay. So, I can take it outside the integral. So, I get 1 over square root of 2 pi, and so I get e to the minus alpha k square by 4 alpha. Okay. So, I get e to the minus k square by 4 alpha, and what I am left with here is minus into infinity to plus infinity e to the minus alpha times I have x plus I k by alpha whole square. Okay. So, now this is nothing but a Gaussian integral, but it is Gaussian shifted by some quantity, shifted by some distance, and we treat this as though it were a real number, and we just use the usual formula for Gaussian integral. So, this integral will be square root of pi divided by alpha. So, the square root of pi will cancel, and you will get square root of alpha divided by 2 or sorry 1 over square root of 2 alpha e to the minus k square by 4 alpha. Okay. So, this is f tilde of k, and this is the Fourier transform of e to the minus alpha x square. Okay. So, this is a Gaussian function, okay, and here actually this involves 1 over 4 alpha, whereas here you had alpha. Okay. That is the difference. Okay. So, in other words, if this was a narrow, okay, of width of inverse width, I will just say inverse width. Okay. So, what that means is that if your initial function is a Gaussian, which so if my f of x is a very narrow Gaussian, so very narrow Gaussian, okay, then f tilde of k will look like a very wide Gaussian. And of course, the if I had chosen this as my Gaussian function, then this would be the Fourier transform. Okay. so just to emphasize what we mean by these Fourier transform pairs is that if f of x is equal to 1 over square root of 2 alpha e to the minus x square by 4 alpha, okay, then f tilde of k is equal to e to the minus alpha k square. Okay. So, this is what you mean by a Fourier transform pair. So, the Fourier transform of this function is given by this function. Now, if I had an x here, then the Fourier transform would be given by a k here. Okay. So, that is what you mean by Fourier transform pairs. Okay. So, I will conclude this lecture by giving a table of a few Fourier transform pairs. So, what we said is that if you had a very narrow Gaussian function, then its Fourier transform will be very wide. So, similarly if you have a very wide Gaussian function, its Fourier transform will be very narrow, and this is generally true that if you have a function which is very broad, then the Fourier transform will be very narrow. You can ask the question, what happens if function is very broad? Okay. Very as in very broad. So, what I will say is that your alpha tends to 0. So, if you take e to the minus alpha x square, alpha tends to 0. So, what you would expect is that as alpha tends to 0, your Gaussian function will look like this. So, it will look like this. That is what it is going to look like. Okay. And now, you can show that the Fourier transform of this will also look like a Gaussian, and it will look like this. So, as alpha tends to infinity, f tilde of k tends to infinitely spiked function, and this is such an infinitely spiked function is referred to as a Dirac delta function. So, it is related to a Dirac delta function. Okay. Now, so let me define the Dirac delta function. Delta x equal to 0 if x not equal to 0, equal to, well, we will say equal to infinity if x equal to 0. Okay. So, that is an infinitely spiked function, but there is another condition. Okay. So, it goes to infinity. Now, it is still treated as though it is a continuous function, and integral delta of x dx from minus infinity to plus infinity, this is equal to 1. So, area equal to 1. Okay. So, this is the definition of the Dirac delta function. Okay. You can also have a Dirac delta function centered away from x equal to 0. So, for example, you can have delta x minus a. Okay. So, delta x minus a. Okay. So, if this is my a, okay, then the function will look like this. It will be spiked at x equal to a. So, Dirac delta function, we have already seen this in when we were doing special functions. Okay. So, we have already seen the Dirac delta function as a derivative of the so recall from special functions. So, when we did special functions module, okay, we did Dirac delta function as derivative is derivative of step function. okay. And we also said that it is defined under the integral. So, delta x minus a f of x dx from minus infinity to plus infinity is equal to f of a, and we also said that you only need to do this integral from I mean, because when x is not equal to a, this will be exactly 0. So, the only contribution will be from a region a minus delta to a plus some small interval delta. In that small interval, then you will get f of a. Okay. So, so the Dirac delta function actually appears very naturally when you are dealing with Fourier transforms, and what is done is you, since the Dirac delta function is only defined under the integral, what is done is suppose you have f of x equal to constant, equal to a constant. Now formally this is not absolutely integrable. Okay. So, formally not absolutely integrable, okay, but nevertheless we define f tilde of k equal to delta of k. So, if I choose this, okay, now you can see that integral e to the I, well, okay. So, let us work this out. So, f tilde of k is equal to integral e to the I k minus I k x into a dx from minus infinity to plus infinity with a factor of 1 over square root of 2 pi. Okay, there should be, I think. So, now this is equal to 1 over square root of 2 pi. Let me just write this is proportional to this. Okay. So, it will turn out to be proportional to this. Okay. Now, if you just write it in this way, okay, then what you have is a integral e to the minus I k x dx from minus infinity to plus infinity. Okay. So, this is equal to a by square root of 2 pi. Now, what you have here is you have an integral. Now, if you just think, if k is not equal to 0, okay, then this looks like e to the minus I k x divided by minus I k. Okay, this is for k not equal to 0. Okay. Now, if we in general k is complex. Okay. So, if we assume imaginary part greater than 0. Okay. So, if we just assume that the imaginary part of k is greater than 0, then what happens is this will have e to the minus, so imaginary part. So, if I write k is equal to k r plus I k I, then what you will have is you will have a term here that looks like e to the minus k I x, okay, where k and k I is greater than 0. So, what will happen is that as this goes to infinity, this will go to 0. Now, this is a so if you go with this assumption, then basically you can show that this is equal to 0 if k is not equal to 0. So, this integral goes to 0 if k is not equal to 0. So formally can be shown that so integral goes to, so I will write f tilde of k equal to 0 if k is not equal to 0. If k equal to 0, then f tilde of k is equal to integral a dx from minus infinity to plus infinity equal to infinity, okay, 1 by root 2 pi. So, formally what we do is that we can also verify what the integral of f tilde of k is. Okay. So, what we will write is that we will write f tilde of k, okay, as 1 by root 2 pi delta of k. Okay, so, this is a function that or I should put an a here, a by root 2 pi delta of k. Okay. So, this is Fourier transform of a constant function. Okay. So, this is how delta function, the Dirac delta function appears naturally when you are dealing with Fourier transforms. Okay. So, we have seen a few Fourier transform pairs. Okay. So, now in the next lecture we look at other properties of Fourier transforms. Okay. And when we will study them in some more detail, we will learn a few theorems about Fourier transforms. Thank you.